Okay, so in last class we studied about what is enthalpy, what is thermochemistry, right? What is enthalpy of Hello everyone, can you hear me? Yeah, you can hear me now. Okay, so yeah, so we studied about basics of thermochemistry, right? So we will start with revision, then we will study about different type of enthalpies. Okay, so first let's see what we have studied in last class. So before going to any other topic, first let's see what we have revised. Yes, Abhiram? Because of this changing weather, I had to cancel yesterday's class also. So please bear with me. Okay, I might be low. So yeah, thermochemistry. Now we know that. What is the meaning of thermochemistry? In between. Can you hear me? Yes? Okay. So we studied what is thermochemistry, right? It is just net exchange of energy when a reaction is carried out. Now this change in energy might be of many factors, right? Because of many factors. It might be because of formation of compound, neutralization of compound, combustion of compound, or change of one substance into other substance, like phase change and all those things, or breaking of bond, formation of bond, or even because of resonance, right? So these all are the factors which may be, right, led to the change in energy. Got it, everyone? So we will study all the changes, and because of these, there might be different type of enthalpies. Okay. Okay. Just hear myself now. Am I breaking in between for you guys? Because I can't hear myself sometimes. Am I clearly audible? Not now. It is getting cut off, right? Yeah, I don't know why it is getting cut off. Okay. Yeah. That's what even I faced, because my internet is fine and voice is very clear, but it just breaks in between. Okay. Okay, let me know when it breaks. Okay. Okay. So yeah. So we study two type of reactions. First, yeah. So the first type of reaction was exothermic reaction and endothermic reaction. I hope all of you remember what is exothermic reaction, what is endothermic reaction. Exothermic reaction is a reaction in which heat energy is released, right? Heat energy is released. Okay, so if heat energy is released, yeah, it broke. Yeah. I just changed the network. Okay, so in exothermic reaction, I can say that heat energy is released, which means that energy of product, enthalpy of product will be less than enthalpy of reactant, right? Right, everyone? Is it fine? My voice is fine now? There's some lag, I guess. Yeah, there was disturbance. Okay. Okay, it's fine now. Don't worry, I'm hearing myself. Okay, I'm hearing myself, so I'll let you know. I'll just change the network whenever there will be issue. So I can say that since energy is released, just think about this. Since energy is released, energy of reactant should be more than that of the product. Yes or no? Just think about this, right? Okay. Now, if energy of reactant is more than that of the product, what do you think will be the sign of delta H of reaction? Tell me. Because we know that delta of H reaction is total enthalpy of product minus total enthalpy of reactant. Right? Right, everyone? Now, because of exothermic reaction, energy is released, which means this energy of reactant is more than that of the product. Right? So it will be less than 0. Got it? Got it, everyone? Students generally get confused about the sign, but if you ever get confused about sign, just think about the basic definition. Okay? In the same way, when you talk about endothermic reaction, right? Then the enthalpy of product will be greater than that of the enthalpy of reactant. So in that case, delta HR of a reaction is greater than 0. Got it, everyone? Tell me, got it? Right? Okay. So I guess everyone got this. Okay? Okay. Okay, everyone. Now, what is standard enthalpy of reaction? That is your delta H that we have already studied, right? What is delta H? Delta H is still not audible. Yeah, it's fine. Yeah, yeah. I don't know what happens because I guess we have 3 Wi-Fi on, like TP-Link, Kestel, BSNL as well as my Geo. So I don't know what's happening. But the internet is fine. Internet is like 30 Mbps. Okay, it's breaking in between though. Okay, so yeah, so we know that enthalpy, standard enthalpy of reaction, is your net change of enthalpy for an overall reaction, which is sum of enthalpies of product minus sum of enthalpies of reactant, right? That we have seen in last class, right? So let's see what are the factors which will affect this enthalpy, right? Just think about this. The first yeah, it broke again. Yeah, yeah. Voice is clear. It's like it's breaking in between. I don't know why. Okay, because internet is fine. So we will talk about the factors which will affect the enthalpy, right? So basically these are the factors on which the energy change can take place, right? So just think about it. Just think about it. Okay, what are the factors on which this energy change can take place, right? So the first, okay, if you think about it, first would be the physical state, right? Got it? For example, see this example, right? See this example. In this case, H2 and O2 are combining to form H2O, right? But are they same? Are these reactions same? Tell me. We have discussed this, right? Is this reaction same? No, right? Yes, very good. They are not same, right? I can say that. I can say that this reaction and this reaction, right, is not same because this is your standard enthalpy of formation of H2O. This first reaction is your standard enthalpy of formation of H2O. Yeah, yeah. Can you hear me now? Can you hear me? Tell me, can you hear me? Yes? Okay. So whenever I see voice is low, yeah, I know voice is low. It should be fine now, right? So I'll just switch to laptop and phone whenever my voice will be disconnected. Okay? Okay. I don't know what is the issue today because of weather. So we have studied that this is your normally, if you balance it, okay? If you balance it, right, will be the enthalpy of formation of H2O, right? But the second one is enthalpy of formation of H2O plus enthalpy of vaporization, because this liquid H2O, okay, this liquid H2O is converted into gas, okay? Liquid H2O is converted into gas. Got it? Right? Now tell me, is this an exothermic reaction or endothermic reaction? Tell me, is this exothermic reaction or endothermic reaction? Exothermic, right? Yes, very good, because delta H is negative, right? Delta H is negative, right? Now tell me, this reaction, H2O, liquid, changes into H2O gas. This is your exothermic reaction or endothermic reaction? Tell me, this is your exothermic reaction or endothermic reaction? Very good. This is your endothermic reaction, right? How can you say? See, in case of first reaction, delta H is more negative, okay? In case of second reaction, delta H is less negative, means some energy is being added, right? Being added. Got it? That's why it is reducing. Now, if I ask you, what is delta H of vaporization? How can you find it? Tell me. It will minus 241.82, 241.82 minus of minus 285.83. Got it, everyone? Hess law. I hope everyone remember Hess law, right? Okay. Okay, everyone. So this was the first factor, which is your physical state. Okay. Now, depending on that, there will be different type of reactions. Okay. Now, second thing, if you remember, whenever we discussed enthalpies, we calculated it for 1 mole. The standard enthalpy was for 1 mole, right? Because obviously, the energy change will also depend on the quantity. If you take 1 mole or 2 mole or 3 mole, do you think that the enthalpy change will be same? Just think about this. Do you think that enthalpy change will be same? Will it be same? No, right? No, no, right? That's the thing. That's why we calculate standard enthalpy for 1 mole. Okay, right? Now, electropic quantification, again, if we have different allotropes, then there will be different energy. Temperature, same thing. Okay, if reactant or reaction is carried out at different temperature, the change in energy will be different. Okay, now pressure volume we have already studied. Okay, that is the basic definition of enthalpy change, which is change in internal energy plus P delta V. So this is the modified equation. We have already studied what is the actual equation, and since we carried all the reaction, most of the reaction is carried under constant pressure condition. That's why B delta P is, tell me, ignored, right? It's 0. Okay? So see, okay, I have already shared this notes. Okay, I have already shared this notes on the Google Classroom. Okay, everyone?
Okay, everyone.
Okay. So Hess law of constant heat summation. Now we have already studied what is your Hess law. So if we have multiple reactions, right? If we have multiple reactions, just see this. Just see this. We have this reaction C plus O2 plus NH3. Okay. C plus O2 plus NH3. Now this reaction is carried out in two steps. First is C plus CO2 will give you CO2. C plus CO2, C plus O2 gives CO2. Right? This is your reaction 1. Then the CO2 plus NH3 will combine to give something. Okay? Right? Amide or something. Okay? So I can say that the overall reaction is sum of these two reactions. Okay, everyone, that is a Hess law we have already studied in yesterday's class or last class. Okay, right? This is we have already studied in last class. Okay. I'm just revising what we have studied in last class. Okay. So till now, we just revised whatever we have studied in last class. Okay, I'm not teaching anything new for now. I'm just revising what we have studied in last class. Right, everyone? I hope all of you remember these. Okay. Okay. So enthalpy of formation. So this we studied. Okay. See, Hess law is basically when you have two or more reactions, and you are adding or subtracting the reactions to get your final reaction. The energy of individual reactions are added and or subtracted respectively. That's it. For example, I gave you this example. Suppose I'm having a reaction. A gives B, and we have delta H1 as enthalpy, and B gives C. Again, delta H2 as enthalpy. Change for these two reactions. But if I have to find A gives C, so for this reaction, delta H reaction is sum of these two, delta H1 plus delta H2. Okay, right? Please watch videos of classroom after the class. Okay, because we have already cleared and solved problems on these concepts. Okay. Okay. So enthalpy of formation, as we studied in last class, enthalpies of formation is basically the heat absorbed or evolved when 1 mole of substance, right, is formed from its constituent elements, right, under constant temperature and pressure. I hope all of you remember this. Yes, tell me. Got it? Right, I'm just revising this. So see, this is your problem. Just try to solve this problem. Just try to solve this problem. Okay, so I'm just showing you this. Okay, right, try to solve this problem, everyone. Please try to solve this. Calculate the standard heat of formation of carbon disulfide. Okay, carbon disulfide, and what is given? Standard heat of combustion of sulfur, carbon, and CS2 is given, right? Just think about it and try to solve. Please try to solve by yourself once. So I guess at least some of you have tried. So see, what is given? First of all, these reactions, right? These reactions are given. Okay, this is already given. Because you know what is the combustion reaction. These are your combustion reactions. Okay, these three are your combustion reactions, which is given as 393, okay, minus 293 and minus 1108.76. So actually this is also minus. Okay, so this is heat of combustion, so it would be minus. Okay, you have to think about this. Okay, this is would be negative, right? Because combustion is your endothermic process, right? Combustion is your exothermic process, my bad. Combustion is exothermic process now, right? Okay, now you have to find the heat of formation of CS2, which is your this reaction, this reaction. Now just think about this. Just think about this. How can you modify? How can you modify this equation to get this equation, right? Just think about this. So let's see what is your reactant. Reactant is this carbon and this sulfur. Okay, okay, very good. So this is your reactant, but this is 2s and this is s gas, right? Okay, so there's again this is mistake. This should be s solid only. Okay, s solid only, right? Okay, right? Now what we have to do, just think about this, what we have to do in order to get this. So just multiply this by 2, yes or no, right? Multiply this whole reaction by 2 to get this reactant. Okay, but again we have this O2 as okay, as well as this CO2 and SO2, right? Okay, so we have to remove this also. We have to remove this O2 and CO2. So if you can see this, if you can see this, we have CO2 and SO2 in this product. Okay, in this product, right? So let's do one thing. 1 plus, we can write like this, reaction 1 plus 2 into reaction 2 minus reaction 3, right? Do this, try to do this. So let's see, carbon solid plus O2 gas plus 2 sulfur solid plus 2O2, right, minus CS2 minus 3O2, right, gives CO2 plus 2SO2 minus CO2 minus SO2. Got it, everyone? Now again, this is balanced reaction would be 2SO2, right? Just think about this. Balanced reaction would be 2SO2 now. Okay? So this reaction is not balanced, but you can balance it. Okay? So minus 2SO2. Got it, everyone? Tell me, got this? Yes or no? Just message me. Did you get this? Yes or no? Now just see the reaction, right? See the reaction. Okay. C solid plus now this O2 gas plus 2O2, right? O2 plus 2O2 gives 3O2, right? O2 plus 2O2 gives 3O2. So cancel, cancel, right? Cancel. Okay. Now this is 2s, 2s, solid. Now this SO2 is negative, so it will go this side. Okay. Now this CO2 and this CO2 will get cancelled. Yes or no? And this SO2 and this SO2 will also get cancelled. So it will give you CS2. Got it, everyone? Tell me. Yes? Yes or no? Right? So according to Hess law, what is the delta H of reaction? So I can say that delta H of reaction is equal to delta H1, this is delta H1, plus 2 delta H2, 2 delta H2 minus delta H3. Yes or no? Tell me. Yes or no? Everyone got this? Everyone got this? Okay? Okay, everyone? Just check your answers. Okay? See your answer. That's what we did. Right? I explained this in a single step. Right, everyone? This is what we did. So the answer is minus 128 kilojoule. Everyone got this? Tell me. Everyone got this? Okay. Yes, we will discuss more questions, Karishma. Don't worry. Right? Okay. See, the terminology will change. Otherwise, the concept would be same. As I told you, depending on the type of reaction, there will be difference in name, but concept would be same. Okay. That's why I taught Hess law before. Right? So we studied what is enthalpy of formation. Okay. So according to enthalpy of formation, the enthalpy of formation of any compound in its natural state is always 0, right? Got it? Okay. So this is what we have studied, that net change, net enthalpy of formation of any reaction is sum of heat of formation of product minus sum of enthalpy of formation of reactant, or heat and enthalpy both are same. That's why I'm just using any of the two. Okay. So example, I've already given you this example in last class. Suppose I'm having A mole of compound A plus B mole of compound B, right? It is giving C mole of compound C and D mole of compound D. So according to my basic enthalpy theory, net enthalpy of reaction is enthalpy of formation of product minus enthalpy of formation of reactant. Yes or no? Tell me, yes or no, right? And net enthalpy, okay, right, is not equal to, net enthalpy is of total moles, okay, right? It's not per mole, right? But standard enthalpy of reaction is per mole. Okay, that's what you have to understand. Okay, for example, see this reaction. See this reaction. Everyone, can you see this reaction? CH4 plus 2O2 gives CO2 plus 2H2O. Yes or no? Tell me. Yes or no? Yes. Now this is also your combustion reaction. Yes or no? This enthalpy of reaction is actually your combustion reaction, because this is reaction is your combustion reaction. But the concept of enthalpy reaction would be same. So it would be heat of formation of CO2, right, plus heat of formation of H2O, or 2 into heat of formation of H2O, right, minus heat of formation of CH4 plus heat of formation of O2, or 2 into heat of formation of O2. Yes or no? Tell me. This will be your enthalpy of reaction, heat of formation of CO2 plus 2 into heat of formation of H2O minus 2 into heat of formation of O2 plus heat of formation of CH4. Yes or no? Tell me. Yes or no? Right? Okay? Okay, everyone? Now, if you find net heat of a reaction, okay, that would be termed as heat of combustion because this reaction is combustion reaction. Okay, they're not anything else. That's why the net change in enthalpy of a reaction may be heat of neutralization, heat of combustion, anything depending on the reaction, but concept is same, this concept only, except for the bond energy. Okay, only bond energy will be different, otherwise every energies will be same. Okay, got it everyone? Tell me, got it? Yes or no? Everyone got this? Right? Okay, see, okay, okay everyone. Okay, everyone. So I guess all of you got this. So next we studied about enthalpy of combustion. So this is, we studied that amount of energy released, right, when 1 mole of substance react with required number of or required mole of oxygen. Got it? Yes or no? Right? Everyone remember this? Okay. So even in this case, we have to find net enthalpy of reaction, which is enthalpy of formation of product minus enthalpy of formation of reactant, as we see in case of CH4 in this example, right? Okay, okay everyone, tell me. I hope all of you remember, because in last class we have solved one problem based on this. So everyone is clear about enthalpy of formation, enthalpy of combustion, right? Okay, because we have studied 4 types of enthalpy in last class, right? Okay. So see, if you know the enthalpy of formation of any product or any reactant, right? You can find the enthalpy of combustion. Okay. For example, see this. You have to find the change of enthalpy of this reaction. Just think about this. Forget about everything else. Forget about this thing. Okay. Forget about this thing. Right? You have to find the change in enthalpy of this reaction. Okay. So see, as I said, the enthalpy of this reaction, the enthalpy of this reaction is enthalpy of product minus enthalpy of reactant. Tell me, yes or no, right? Yes, Karishma, the voice would be low because when I get disconnected, I just switch it. Okay. Okay. Right. So what can you say? What can you say about this? Can I say this? Delta H of a reaction is equal to heat of formation of product, summation of heat of formation of product, or see, in this case, right, it is heat of combustion of these products minus summation of heat of combustion of reactant. Yes or no? Tell me. Can I say that? Can I say that net heat of reaction is equal to heat of combustion of, right, combustion of product minus summation of heat of combustion of reactant? Yes or no? Tell me. Yes or no? Right? Got it, everyone? This will be given. Okay. The heat of combustion of CH4, C4H8, C2H6, C6H14 would be given, right? Okay, everyone. Okay, and even if it's not given, even if it is not given, you can calculate, right? Okay, depending on the problem. So I hope all of you are getting how to use Hess law, right? So see, this is what I told you, right? Heat of a reaction is heat of combustion of C6H14. Wait. Okay, sorry, my bad. Right, my bad. It is exothermic reaction, right? So in this case, net heat is released. Net heat is released, right? So it will be total heat is released. So obviously, heat of combustion of this would be more than that of this, right? Okay. So this is, you have to remember, heat of reaction. In case of combustion also, it is heat of combustion reactant minus heat of combustion product, right? So bond energy plus this one, because it is your exothermic reaction, it should be negative. Okay. So if you see this reaction, so C6H14, right? So just write the reaction, separate reaction, right? Write the separate reaction. C6H14 plus we have 9.5 O2 gives 6 CO2 plus 7 H2O, right? This is your first reaction. Now second reaction would be C4H8. C4H8 plus 6 O2 gives 4 CO2 plus 4 H2O. Okay. Then we have C2H6 plus 3.5 O2 gives 2 CO2. 2 CO2 plus 3 H2O. Got it? This is your reaction. This is your reaction. So we have delta H1, delta H2, delta H3. Okay, right? So if you see this overall reaction, okay, right? So it is this minus this and this, right? And now overall reaction, because it is just the sum. Overall reaction is H1 minus H2 minus H3. Yes or no? I'm just using Hess law, right? Think about this. This reaction is your H1 minus H2 minus H3. Delta H of the reaction would be this now, right? Tell me. So here we are using Hess law, right? Here we are using Hess law. That's why it is heat of combustion reactant minus heat of combustion product. Okay. Are you getting this concept? Tell me. Are you getting this concept? It is not exception. It's just that in this case, we are just using Hess law, right? Okay. Got it, everyone? Tell me. All of you got this? I explained it. Okay. Right? Because this reaction is using Hess law. It is the sum and difference of these three reactions, right? H1 minus H2 minus H3, right? That will give you this reaction. So according to Hess law, it will be H1 is heat of combustion reactant and H2 and H3 is your product. Okay, everyone, right? Okay. See, this is very easy if you understood it. Okay. Okay. Now this is what I have told you that it will be taught in school. Okay. Or you can just read through your NCERT. It is your bomb calorimeter. Now this configuration, right? This is a constant volume bomb calorimeter. Okay. Now this is used in order to find internal energy. Constant volume bomb calorimeter is used to find internal energy, right? And constant pressure bomb calorimeter is used to find enthalpy. Okay. So please go through this. Please go through this. This will be useful for your school examination, right? We have already studied the basic formula, which is Q is equal to MC delta T. Okay, right? So when you talk about J or NEAT, we can solve this problem using this formula MC delta T that we have already studied. Right, everyone? Okay? Okay, everyone. Okay, so till now we have studied about what? Tell me, what is enthalpy? What is enthalpy of formation? Enthalpy of combustion, right? Next is bond enthalpy. Okay, now try to understand this. I hope all of you have clear understanding of enthalpy of formation, enthalpy of combustion. Tell me, and Hess law. At least these three should be very clear, right? Yes, everyone, tell me. Are you clear about this? Because if you can actually think what is happening, right, it will be easy. Now just think about this, right? This notes is already shared, so if you want to read, you can just read afterwards, but just listen to me, okay? Everyone please focus on this reaction. So we have 4H, by the way, okay, right? Or it will be 2H2, okay? Now just think about this. In this case, in this reaction, what is happening? Tell me. In this reaction, what is happening? Just imagine what is happening. We had this carbon, then we had H, right? H. Okay, suppose it is H atom. So these two atoms will come together, yes or no, right? In order to form a bond, they will come together and form a bond. Yes or no? Tell me, yes or no? Yes? Now, if they are coming close, if they are coming together, what will happen to their potential energy? It will decrease or it will increase? Tell me, will it decrease or will it increase? I hope all of you remember the concept of bond formation, right? In chemical bonding that we have studied. Yes or no, right? That a bond is formed when energy is decreased. I hope all of you remember this concept. How many of you remember this graph? Tell me. This is bond energy graph. Everyone should remember this, right? That if you bring two atoms closer, right, the energy will decrease. It will be minimum, right, at a point which is its bond length. Okay, I gave you the example of spring, that if a spring is expanded, it will try to come to its natural position, right? And if you push it, then also it will try to come to your natural position, right? Okay, now tell me, if you form a bond, energy is released or energy is absorbed? Tell me, energy is released or energy is absorbed? Released, yes, because energy is decreasing, right? Energy is decreasing. So if energy is decreasing, right, it is released. Okay, right? So I can say that, see this is very important concept. In this case, how many CH bond is formed? How many CH bond is formed? Tell me, how many CH bond is formed? 4, right? 4 CH bond is formed. Now this delta H is for this whole CH4. Okay, so if I ask you, what is the bond energy of CH bond? CH bond, tell me, what is the bond energy of this CH bond? Then what it will be? It will be this total energy divided by 4. Yes or no? Right? Because this energy is energy released when 4 bond is formed. Okay. So in order to break this 4 bond, you have to give this much energy. Right? So in order to break 1 bond, you have to give this by 4 energy. Right? And since I'm saying give, so it will be positive. Got it? Right? Because in order to break a bond, you have to supply energy. Yes or no? In order to break a bond, you have to supply energy, right? So I can say that, right? I can say that bond strength or bond energy is your energy required, right? Energy required to break 1 mole of bond of one particular type, right? Okay, got it, right? Okay, so in nutshell, you can say it is average energy needed to break 1 mole of particle bond in a gaseous molecule, okay, to convert it into gaseous atom, as simple as that. Got it, everyone? Tell me, got it? Bond energy, right? Everyone got this? Because there's another type of energy that will be confusing, okay? That's why you should be very clear with the definition. As I told you, you should be very clear with the definition, okay? Right, everyone? So let's see some more cases, some more examples. Okay, so let's see here, right? As I told you that this bond energy is also reactant minus product. I hope all of you remember, right? I hope all of you remember that this is your reactant minus product instead of product minus reactant. Okay, okay. Now let's see, we have this reaction C2H4 plus H2. C2H4 plus H2 is giving you C2H6, right, everyone? Okay, right? But before converting to this, it has to, because I told you that bond energy is the amount of energy required to break or amount of energy released to form a bond from individual gaseous atom. Yes or no? Tell me, yes or no? I will tell you why this is reactant minus product. Okay, because it's not that it is breaking the law. It is not breaking the law. There's a reason for that, right? So if you see this, just try to break down all the reactions. So first, there should be enthalpy of formation of this C2H4. Yes or no? So if you break down this reaction, it will be 2 carbon plus 4 hydrogen. Yes or no? So suppose it is H1, right? And this H2 is also your 2H. Suppose this is H2. Yes or no? Tell me. Yes or no? Right? Now, if you break down this one, it will be C2 plus C6 gives 2C plus 6H. It is also like H3. Now, do you think, isn't it same as heat of combustion where we are actually using Hess law? Tell me, isn't it same as that where we are actually using Hess law? Because overall reaction, which is your this reaction, is nothing but H1. See, this reaction is H1 plus H2 minus H3, right? Delta H total. Tell me, right? Agree? Just think about this. Agree? This is same as what we have done with combustion reaction, right? We are just using Hess law, है ना? So if you see this, this is H1 plus H2, which is your energy of bond energy, because we are breaking the bonds into components, right? Got it? Okay, everyone? Tell me yes or no? Yes or no? Right? Okay? Okay, everyone. Now just think about this. Just think about this. Here, how many bonds are being broken? Because see, if you see this reaction, it is not CH bond. We have CC bond also. Okay, we have CC bond also, right? So you have to think about this, right? So first we will just talk about this one, total heat of reaction. Then we'll talk about H1, H2 and H3 separately. Got it? So you understood this, how delta H of a reaction is H1 plus H2 minus H3, which is total bond energy of reactant minus bond energy of product. Yes, everyone got this one at least? Tell me, everyone got this concept? Just raise your hand. Okay, very good, everyone. Right? Now let's see H1, H2 individually. Right? First of all, let's see H1. Now this is your H1. Now if you see this, C 2H4, right? This is your CCH, H, double bond, H, H. Yes or no? Tell me, yes or no, right? Agree? So I can say that in this case, I'm having 4 CH bond, right everyone? And 1 C double bond C bond, right? Right everyone? So total amount of enthalpy to break this bond is 4 into bond energy, 4 into bond energy of CH bond and 1 into bond energy of C double bond C bond. See, you cannot say that C double bond C bond is equal to 2 C single bond. Okay, because double bond and single bond have different energies. Got it? So you cannot say that, right? You have to keep that in your mind. It is 1 C double bond C bond. It's not 2 C single bond. Okay, right? So this is about C2H4, right? Now H2 is simple, but when you talk about C2H6, just see the diagram, right? This is your 6 CH bond, right? And 1 CC bond. Now this 1 CC bond is single bond. Okay? So it will be bond energy of CC bond plus bond energy of 6 or 6 into bond energy of CH bond. Got it everyone? Tell me, got it? Yes or no? Yes or no? Okay, so I can say that when you talk about reactant, okay, when you talk about reactant, right, this is E, bond energy of CC bond plus 4 into bond energy of CH bond, right, plus bond energy of HH bond, okay, minus bond energy of 6 CH bond and CC bond, right? Here it is missing, right? H2 is missing, E, HH is missing. Okay, it might be 0, but we don't know. We have to write. Okay, okay, everyone, got this? I hope all of you understood. Everyone, all of you understood this? Yes or no? Just raise your hand if. Okay, very good. See, because it is just concept, everything is same. Either you are using Hess law or you are using delta H, right? Since in this case it is being added, it is not the heat of formation of product, na? Because if you remember this delta H wala, it is used when heat of formation of product and reactant is given, right? But it is not the same case, na? Okay, okay, everyone, right? Now next is resonance energy. Okay. Now, I hope all of you know what is resonance. All of you remember what is resonance. Tell me, is there anyone who don't remember what is resonance? Except Akshay? Everyone remember, right? Okay. So I can say that we know because of resonance, the molecule become more stable. Yes or no? Because of resonance, the molecule become more stable. Right? Yes, everyone? Okay, very good, very good. Now, if it become more stable, then the energy should be less as compared to its theoretical value. Yes or no? Right? Got it? So I can say that your resonance energy is actually the energy difference, the most stable resonating structure and your resonance hybrid, or you can say that it is the difference in theoretical energy, right, and the actual energy, or actual energy is theoretical energy, which is calculated minus resonance energy. For example, just think about this, right? Just think about it, this. Okay, just think about this. Yeah, Karishma, right? Because I switch to laptop whenever my voice is breaking. Don't worry about that. Okay. So this is your structure of benzene. Tell me, this is your structure of benzene? Yes or no? Right? So what would be theoretical bond energy of this benzene? Tell me, what would be theoretical bond energy of this benzene? So it would be something like this now, right? Just think about this. 3 into C double bond C plus 3 into C single bond C plus 6 into CH bond. Yes or no? Tell me. Tell me. Right? Yes? Right, everyone? So this should be the theoretical values, right? But because of resonance, because of delocalization, the energy will be less than this calculated energy. Okay, and that difference is your resonance energy. Got it, everyone? Got it? You understood what is your resonance energy, right? Okay, so you have to think about this. Resonance energy, right, is the difference between actual and theoretical, right? Okay. Okay. Or you can also say that it is resonance energy of product minus resonance energy of reactant. Okay, everyone? Right, everyone? So this is something that you have to remember. Okay? Okay. Now let's see. Let's see. We have A plus B gives C plus D. Okay. Right? Where B have this resonance and D is having resonance. Right? So net energy change. Net energy change, what it will be? Tell me, what will be net energy change? It is delta H actual minus delta H theoretical, as we said. As we said in this, it is delta H actual minus delta H theoretical, right? Which is equal to resonance energy product minus resonance energy of reactant. Okay, because when you talk about delta H of a actual, so it is bond energy of A plus bond energy of B, right? Okay, minus resonance energy of B minus resonance energy of B minus bond energy of C minus bond energy of D and resonance energy of B. Yes or no? Tell me, yes or no? Okay? Okay, everyone. So, if you see this, this is your actual. Theoretical would be EA plus EB minus EC plus ET. Got it? This would be your theoretical. Yes or no? Tell me. This energy would be delta H theoretical, right? So if you take to this side, it will become this. And this will be your delta H, right? Actual minus delta H theoretical is equal to resonance energy of product minus resonance energy of reactant. Okay, so this is how we prove that we have the difference in actual energy minus theoretical energy giving us difference in resonance energies. Got it? Right, everyone? Got this? Okay. So everyone, please note this down. Okay. Because people generally get confused about this. In some book, it is given wrong. Okay. Just think about this. Because of resonance, stability is increasing. So energy will decrease. right? If energy will decrease, then the actual energy will be less than the theoretical bond energy. Yes or no? Just think about this. Logically think about this. Yes, that's why it is theoretical bond energy minus resistance energy. Okay? Okay, everyone? Okay, everyone. See, my voice is breaking. That's why I'm switching to laptop. That's why it might be slow in between. Don't worry about that. At least it's better than broken sound. Okay? Okay. Okay, everyone. Okay. So we have discussed this bond energy, resistance energy till now. Right, everyone? The next is enthalpy of solution. Okay. Now just think about this. Right? I'll just use this reaction. Because we have already studied this enthalpy of solution. We have already studied enthalpy of solution, right? How many of you remember this? Tell me. How many of you remember enthalpy of solution? What is the meaning of enthalpy of solution? Tell me. What is the meaning of enthalpy of solution? Anyone? Can anyone tell me? What is the meaning of enthalpy of solution? When 1 mole of any substance is dissolved in solvent, the amount of energy required or released is called your enthalpy of solution. Yes, hydration energy you remember? Tell me. At least you remember hydration energy, right? So it is same now. Okay, right? So when you talk about any ionic compound, just think about this. Any ionic compound, it is dissolving in water, right? Either it will release energy or it will require energy. Now, we have studied in chemical bonding that this process is actually of 2 steps, right? Just see this. Suppose I'm talking about NaCl. Just talk about NaCl. NaCl plus H2O, right? Gives NaCl dot H2O, right? So what is happening over here? The first step, step 1, I hope all of you remember, is conversion of NaCl into its ions, Na plus Cl minus. Got it? So this is your ionization, and this energy is called as lattice energy. Lattice energy. How many of you remember this? Because we are breaking this NaCl lattice, right? So this is your lattice energy. Now this Na plus, and Cl minus. Now since it has become your ions, it will be attracted by H2O. ठीक है? Right? Right? And this process is called as hydration. This process is called as hydration. ठीक है? So I can say that when you talk about total energy, ठीक है? Total energy, it is your sum of hydration energy and lattice energy. So delta H solution is equal to delta H lattice plus delta H hydration. Yes or no? Tell me. All of you remember this? Yes? Yes, very good, Karishma. So I hope all of you remember this, right? Okay. Okay. So let's see. So in the same way, in the same way, we have two types of energies, lattice energy as well as hydration energy. So in order to any compound to dissolve, right, heat of solution should be negative. Yes or no? Right? Heat of solution should be negative. Delta H should be negative. So lattice energy should be less than hydration energy. Right? So that's the thing. If lattice energy is more than hydration energy, right, enthalpy of solution is positive. And if lattice energy is less than hydration energy, then it is negative. And in order to salt, sorry, in order for this salt to be freely soluble, okay, right, delta H should be negative, right? But again, because of some exceptions, when temperature is increased, because we know that now delta G is equal to delta H plus T delta S, sorry, minus T delta S, right? So even if this is positive, but if this term will become more negative, right, then also it will be dissolved. Got it? Right? Can you give me one example for this? Tell me. If you increase the temperature, right, then your sugar is dissolved. Got it? More sugar can be dissolved if you increase the temperature. Yes or no? Tell me. Right? Okay? Okay, everyone? Okay. But usually, under normal circumstances, you can say that hydrogen should be more than lattice energy for dissolution. So we have already studied what is enthalpy of hydration. Yes or no? I hope all of you remember enthalpy of hydration, right? Right, everyone? So basically, see this, CuSO4.5H2O, right? CuSO4.5H2O. Now, if this H2O is attached to this copper sulfate, then the amount of energy released is your delta H hydration, right? So this is your anhydrous plus this H2O, it will be attached, then this delta H is your energy of enthalpy of hydration. Got it, everyone? Tell me, got it? Now this not 5H2O, it is already 5H2O. And this is 795 H2 liquid. Then again, this is your total delta H. So what is the difference between these two? Tell me, what is the difference between these two? Tell me. The difference will give you this using Hess law. Yes or no? The difference will give you this delta H, right, using Hess law. Yes or no? Yes, everyone? Yes, everyone? Okay, right? So combining of H2O is the change of energy when H2O is combined with any salt is your delta H hydration. Yes or no? Everyone got this? Right? Okay, everyone. So last enthalpy of today, okay, enthalpy of neutralization, which we have already studied in last class. So we will just revise this. Okay. Okay, everyone. Take care. Now see, enthalpy of neutralization. So what is the meaning of neutralization? We have already studied that neutralization is a reaction of acid with base to form salt and water, right? It is a reaction of acid and base to form salt and water. Now, when we have this reaction, there's a fixed amount of energy which is released. That is called as neutralization energy, okay, or enthalpy of neutralization. Now, if you see this first reaction, okay, see this first reaction. The same reaction I used in last class. So we have HCl and NaOH. It is combining to form NaCl plus H2O. So I told you that H plus plus OH minus gives H2O liquid, right? For this reaction, delta H is this one. Okay, for this reaction, delta H is this one. So this is already written over here. Okay, right? So how can I say that this reaction and this reaction will have same delta H? Because the definition of strong acid and strong base say that it will dissociate completely, right? Means no energy is required for the dissociation. Means NaOH gives Na plus plus OH minus. It will dissociate completely. Okay. Now it is the dissociation. It is not the breaking of lattice. It is already in aqueous phase. Okay. Got it? There's difference. It is not the breaking of lattice. Okay. Right? Lattice means it is in solid phase. NaOH is already in aqueous phase. Okay. So I can say that net reaction, net delta H neutralization is equal to delta H of ionization that we have already studied last class plus this delta H of combination of H2O, which is minus 57.1 kilojoule. Yes or no? Yes or no? Right? So for weak acid and weak base, there will be some heat of neutralization, right? Sorry, there will be some heat of ionization, which is endothermic. You have to give, you have to give energy to break the bond. Yes or no? Tell me. You have to give energy to break the bond, right? So this is your endothermic process. So there must be some energy which is added plus X, right? So overall energy of neutralization will always be minus 57.1 plus X. Now this X will depend on which acid or base you are taking. Okay, everyone? Tell me. Everyone got this? Yes or no? Everyone got this? Right? Okay? Okay? So we have already explained all these things. Okay? So this is written in notes what I have explained. Right, everyone? Anyone have any doubt? Tell me. Anyone have any doubt? See this example. Okay, if you see this example, it will be clear, right? That energy of neutralization, delta H neutralization, is your delta H ionization plus delta H neutralization of H plus and OH minus. Okay, 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 everyone. Tell me. Everyone got this? Okay, everyone. Tell me. Just raise your hand. Okay, everyone. So last topic is your Born-Haber cycle. Okay. Born-Haber cycle. So just see this. Born-Haber cycle is net energy change in a reaction. Okay. So see. We have Na solid plus half Cl gas gives NaCl. So you have to find what is the energy change for the formation of NaCl, right? Just see this. It is very easy actually. Now just think about this. We know that NaCl is formed by this Na plus Cl minus gives NaCl. Yes or no? Yes or no? Tell me. Step by step. Yes or no? Yes or no? Sorry, my voice was echoing. Okay, right? Okay. I'm repeating again. I'm just explaining this. I'm just breaking down this whole reaction. Now, Na plus can be obtained by Na solid. First, it is solid. It should be converted into gas. Okay. Then this gas. This Na gas should be converted into Na plus electron. Okay, everyone. So this is about Na. Let's see about Cl. So we have half Cl2. First, this has to be converted into 2Cl or Cl, just Cl, because it's already half now. So Cl, Cl gas, right? Then this Cl gas should have gain one electron to form Cl minus. Everyone, these reactions are clear? Tell me, these reactions are clear? Yes or no? So how many reactions can you see here? From this to this, how many reactions can you see? Step by step. How many reactions? 4 reactions, right? Okay, then this is your 5th reaction. So in order to get this, there are 5 reactions. So 5 delta H. So let's see step one by one. Now solid is converting into gas. So this is delta H sublimation. Yes or no? Solid is converting into gas. So this is delta H sublimation, right? Now this is, tell me, what is this? Electron is lost. What is this? Ionization energy? Yes or no? This is ionization energy, right? Okay. Now in this case, Cl2 is broken down into atom. So this is called as delta H atomization, right? Delta H atomization, right? In which bond is broken, or delta H dissociation, doesn't matter, right? And this is your electron affinity. Electron affinity. Last one is electron affinity, right? And this, tell me, what is this? This is your lattice energy. Yes or no? This is your lattice energy, right? So I can say that total change, delta H reaction, is equal to, right, delta H of sublimation, ionization, then dissociation, then electron affinity, then lattice energy. Yes or no? Yes or no? Tell me. Yes or no? See this? Yes or no? Right? So total energy can be calculated, right, by adding all of them. So we know that sublimation energy is provided. Ionization energy is provided, right? Electron affinity, energy is released. Lattice energy, since you are forming bond, it is released. Bond dissociation energy, you have to, tell me, give energy. Got it, anyone? Tell me, right? So see this example, right? We have to find lattice energy of this. Delta H sublimation is given, delta H dissociation, ionization, everything is given. Delta H formation of LiCl is also given, right? So can you find delta H, right, or lattice energy of this reaction? Tell me, can you find this? Because overall reaction is given. See, this is overall reaction, right? Just go through this. Can you calculate the lattice energy? It is just linear equation in one variable. Total energy is also given. Okay. Okay, everyone. Just raise your hand. If you understood this, just raise your hand. Okay, everyone. Right? Okay. Thank you, everyone. So let's see. So this is your summary. Okay. See this. There are 3 other enthalpy of reactions which I have skipped because I have already taught in chemical bonding. Right? We will see which those reactions are. Okay. Now let's see. Let's see this. It will be uploaded within 1 hour depending on the net. So see, we studied enthalpy of formation. See this. We studied enthalpy of formation, enthalpy of combustion, enthalpy of fusion of vaporization, which is enthalpy of phase transformation. Yes or no? Then enthalpy of sublimation. Again, it is phase transformation. These 3 are enthalpy of phase transformation. Yes or no? Right? Fusion, vaporization, sublimation is your enthalpy of phase transformation. Enthalpy of atomization is nothing but your bond dissociation energy. Okay, right? Where you're just breaking the bond and converting into atom. This is just a name given. Enthalpy of reaction is total enthalpy, right? Enthalpy of neutralization, we have already studied. Enthalpy of ionization is ionization energy. Okay, see this. I have skipped these two because we have already studied what is the meaning of enthalpy of ionization and electron gain enthalpy. Yes or no? Ionization energy and electron affinity. I hope all of you remember these two. Tell me. Do I need to explain again what is ionization energy and electron gain enthalpy? No, right? I hope all of you remember this. Yes or no? Just raise your hand. Just raise your hand. Right? Okay, very good, very good. Then we studied what is lattice energy, bond dissociation energy, right? Energy of solution, which is sum of both lattice energy and hydration energy. And enthalpy of mixing is just random, okay? Right? So we are done with this thermochemistry. Okay, we are done with this thermochemistry, right? So if you see the assignment, right? Instead of solving module first, please go through this. Okay, please go through this assignment. There are solved examples. See, we have solved examples. Please try to solve all the solved examples. Okay, before tomorrow. Tomorrow we will discuss in class exercise of 0.3, 0.4. Okay, okay everyone. Right everyone. Okay everyone. Please go